The topic of the talk in this sample video is nuclear and particle physics. Here I will be talking about the basics of nuclear physics. The topic is taken from the CBCS BSc Physics syllabus that is uploaded in the UGC website. Before we discuss the nucleus, let's have a brief look at the atom. About 200 years back, John Dalton for the first time gave the first scientific description of the atom. He proposed that all matter is made up of tiny indivisible particles which constitute the matter. The concept of atom is similar to the brick that forms the house. So the bricks join together, they form a wall, and the walls join together and form a house. The same way, the atoms join together and form a lattice, and the lattice join together and form the matter. Once the concept of atom was well accepted by the scientific community, the scientists wanted to know the structure of the atom. One of the scientists, Ernest Rutherford, did a very beautiful experiment using alpha particles. The concept is similar to the situation where your eyes are closed and you are standing in a corridor. You are given a set of balls in your hand and you are asked to identify if there is an obstacle before you or not. So what you would do is you would take the balls and throw them in front of you. If the balls return back, that means there is an obstacle. Otherwise, the space before you is free. Basically, this idea was used by Rutherford. Instead of the balls, he used alpha particles. Alpha particles are positively charged particles. And he bombarded gold foil with alpha particles. There was a detector behind the gold foil which could collect the alpha particles, and we could analyze the angle at which the alpha particles were scattered by the gold atoms. He found that almost all the alpha particles passed through the gold foil and only very few bounced back. So he inferred that atom as such is mostly empty, with almost all the mass of the atom, or I would say most of the mass of the atom, is concentrated at the core of the atom. Thus, this core was termed the nucleus. Thus, nucleus consists of 99.9% of the total mass of the atom. Since the matter as such is neutral and you have electrons inside matter, the nucleus has to be positively charged. So the nucleus is a positively charged core of the atom with almost 99.9% of the mass in it. Now Dalton has proposed the atom to be the smallest indivisible particle. But we now know that the atom consists of electrons and nucleus. But is that all? No. The nucleus still has constituents. That means nucleus has nucleons. Nucleons are the constituents of the nucleus. So the nucleus has protons and neutrons as its constituents. The protons are positively charged particles with a charge equal to the charge of the electron and a mass of about 1.6726 into 10 raised to minus 27 kilogram. Whereas the neutrons, as the name suggests, are neutral, electrically neutral, but their mass is very close to the mass of the proton. That is 1.6749 into 10 raised to minus 27 kilogram. So we have seen that the Dalton's idea of indivisible atom is not right. So the atom consists of nucleus and electrons, and the nucleus consists of protons and neutrons. Now, before we move further, to analyze the problems in nuclear physics, it would be very nice to have a proper representation of nuclei. The two important numbers that are associated with the nuclei are the atomic number Z and the mass number A. The atomic number is equal to the number of protons and the mass number is equal to the sum of the number of protons and the number of neutrons. A nuclei will be represented by a symbol which will represent the symbol of the element X, and then you have a superscript which will define the mass number and the subscript which will define the atomic number. So here A is the mass number and Z is the atomic number and X is the symbol of the element. In the case of hydrogen, X would be replaced by H and A is equal to 1 and Z is equal to 1. In the case of chlorine, A is 35 and Z is 17. Now we know the nuclear representation. We can now look at the nuclear classification. The first classification are the isotopes. Isotopes are nuclei with the same atomic number but different atomic mass numbers. That means isotopes have the same number of protons but different number of neutrons. An example of isotope would be radioactive carbon-14 and carbon-12. They have the same atomic number 6. That means the same number of protons, but they have different number of neutrons. Another example would be the isotopes of hydrogen. They are protium, deuterium, and tritium. Another classification would be the isobars. Isobars are nuclei with the same atomic mass number but different atomic numbers. That means calcium 40 and potassium 40 are isobars because they have the same atomic mass numbers but they have different atomic numbers. That means different number of protons. So calcium has the atomic number of 20 and potassium has an atomic number of 90. The next classification would be the isomers. So isomers are nuclei with the same atomic mass number and the same atomic number but different states of excitation in the atomic nucleus. So these nuclei have different excited states and these excited states are called the metastable states. As an example of an isomer, we can have a look at the protactinium. The protactinium isomer is represented with an M written along with the mass number, which differs from the protactinium which is stable, which has no M written with the mass number. So the excited state nucleus in course of time comes back to the stable state. The next classification are the mirror nuclei. Mirror nuclei are the nuclei with the same mass numbers, but the proton number of the first nuclei is equal to the neutron number of the second nuclei and the neutron number of the first nuclei is equal to the proton number of the second nuclei, such that the mass number remains the same. That is, A is equal to N1 plus Z1 and is equal to N2 plus Z2. An example would be nitrogen 13 and carbon 13. So nitrogen 13 has the proton number Zn is equal to 7, which is equal to the neutron number of carbon 13. And the neutron number of nitrogen 13 is 6, that is equal to the proton number of carbon 13, that is equal to 6. So this was the classification of nuclei. Now let's look at the size of the nuclei. The nuclear radius is of the order of 1 femtometer. That's about 10 raised to minus 15 meter. Is sometimes also called a Fermi. The radius of the nuclei is directly proportional to the cube root of the atomic mass number, or R is equal to R naught into A raised to 1 by 3, where R naught is a constant given by 1.2 into 10 raised to minus 15 meter. R naught varies from nuclei to nuclei, but is almost constant for atomic numbers greater than 20. Atomic mass numbers that are greater than 20. So you can more or less take R naught to be constant. Yeah? Now next, let's look at the nuclear density. One of the remarkable findings was that the nuclear volume is directly proportional to the number of nucleons that are inside the nucleus. This means that the nucleons are incompressible. So the nuclear density is given by nuclear mass divided by nuclear volume. Now if we consider the nucleus to be a sphere of radius r, and if we know the atomic mass number for the nuclei, then we have seen that we can find the radius by using the formula r is equal to r naught a raised to 1 by 3. And if we take the nucleus to be spherical in shape, then we can easily find the volume of the nucleus as 4 by 3 pi r cube. And to find the nuclear mass, you have to add the mass of the nucleons. So the nucleus consists of protons and neutrons. And as I have shown before, the mass of the proton is very close to the mass of the neutron, which we will take them to be nearly equal in this case, because we just want to get the order of the nuclear density. So we will take that to be 1.67 into 10 raised to minus 27 kilogram. So the nuclear mass can be written as m into A, where A is the atomic mass number. And the nuclear density, as we know, is given by nuclear mass by nuclear volume. So we substitute for nuclear mass as Ma and for nuclear volume as 4 by 3 pi r cube. And if we substitute for R, then what we will get is 3 into m by 4 pi r naught cube. We know m, we know pi, we know r naught. So if we substitute it, we will get the nuclear density to be 2 into 10 raised to 17 kilogram per meter cube. That's huge. So the nuclear density